South Africa, a beautiful country full of diversity and contrast. It has a wealth of mineral resources, but other resources such as water are scarce. Its vast coal deposits ensure that it has the world's cheapest electricity. But due to a troubled political history, these resources were not always made available to the majority of its population. Today, South Africa's growing demand for electricity outweighs its supply.
South Africa's reality is that the electricity demand is starting to outstrip the capacity. We just don't have enough power stations at the moment to supply in the electricity needs of the country. And that is mainly because for the past 20 years, no new power stations were built. And that again was because the country had an oversupply of electricity for many years. The other dilemma that the country has is that most of our power, in fact about 90% of the electricity, is generated in Mpumalanga, where the coal-fired power stations are. They are there because the coal mines are there. Now, to take this electricity to the coast, for instance to Cape Town or Port Elizabeth or even Durban, is quite expensive. You have to build power lines over distances of over 1,000 kilometers. And not only is it expensive, there's also transmission losses. And what that really means is that if, let's say, 100 megawatts are generated in Mpumalanga at that power station, only about 80 megawatts may arrive on the other side of the line.
If the current way of supplying energy in the form of electricity is insufficient, not sustainable, and using up South Africa's precious water supply, what are the alternatives?
South Africa is blessed with a wonderful array and potential of renewable energy sources, in particular solar, which is effectively limitless. There is so much solar installation in South Africa, it's enough to supply all the energy needs of Africa if we could harness it all.
Solar is possibly the one resource that we use least. We have been blessed with significant amounts of solar installation here in Southern Africa. One of the challenges, though, is that those systems are fairly expensive, and that means that it's really middle class and the upper income groups that can use solar water heating, or rather can afford solar water heaters on their homes.
Other renewable resources that we have in abundance include wind.
You do need a fairly strong and very consistent wind to make it worthwhile. If you're going to rely on wind energy, what do you do for backup when there is no wind?
We've also got ocean resources, ocean currents as a source of energy, as well as wave, and there's a possibility of ocean thermal power, which is also being investigated. Micro hydro, that's using run-of-river installations to tap the energy in flowing water.
Well, we do already use hydropower in South Africa. We have 2 dams on the Orange River, at the Gerep Dam and at the Van der Kloof Dam, that do generate electricity from hydropower. South Africa is a very dry country, and our opportunities within the country are really limited. Large-scale hydro, I suspect that we already have built all of the large facilities that we can.
One of the problems that we are facing at the moment is this whole idea of climate change. There was a recent report in February by the International Panel on Climate Change, where they showed that, for example, in Southern Africa in particular, we could, by the end of the last decade of the century, have a dramatic drop-off in our average rainfall by up to 20-30%. So of course that's going to be a big issue. And a lot of environmental scientists and environmentalists are discussing how we can address this issue of climate change. One power source that has come to the fore in this whole debate is in fact nuclear power.
Nuclear energy refers to the process whereby heat is generated from a nuclear reaction. The nuclear reaction normally involves the splitting of an atom and the release of heat. One normally then taps this heat to produce other types of energy. such as steam, and which drives a turbine.
But nuclear power is and always has been a contentious subject. The world reeled at the effect of an accident at the Chernobyl power plant in the former Soviet Union in 1986. It sat up and took notice, and perhaps for the first time, realized that there is no room for error when working with nuclear fuels. So not everyone is as enthusiastic about nuclear power as a solution for South Africa's growing energy demand.
Anytime that you're investing in nuclear power projects, you are increasing the potential for the proliferation of nuclear weapons. There are, of course, a whole lot of more immediate reasons for people who might be living in the neighborhood of a nuclear power plant, and that is, number one, the risk of some kind of accident. We have Chernobyl as the example of what can happen with the kind of reactors that we have in Koeberg at present. That kind of a meltdown is the worst case scenario. There are very many other potential accidents like that in Tokaimura in Japan a few years ago, where a couple of workers were killed. What we find with nuclear power is that you can never rule out human error. So no matter how carefully you design the plant, how carefully you design your systems, it is always reliant on not making any mistakes. And human beings make mistakes.
The big concern about nuclear power and the generation of electricity using fission reactors, for example, now, is there are two things. The one is the accident scenario. If you have an accident, serious accident, there'll be a large impact on an area around the nuclear power station. So that is an accident scenario, and there's a big concern of that. And the other is, in fact, the concern over the disposal of high-level waste that is produced in the production of electricity using fission reactors. Now, one fission fragment that people may be familiar with is cesium-137. There's been a lot of talk about cesium-137 because it has been produced in the detonation of nuclear weapons, for example. This radioactivity, including the cesium, then got dispersed around the globe, and it gets deposited by, for example, precipitation, like rain, and it gets embedded in the soil. Another source of cesium, of course, was the Chernobyl accident that happened in 1986.
Of course, it's the controlled nuclear reaction that produces the radioactivity that constitutes the public health risk of nuclear power plants, both in terms of the routine radioactive releases, mostly through cooling water that goes off into bodies of water. In the case of Koeberg, that's into the ocean, but in the case of French reactors, that is in rivers, also into the atmosphere. And then you have accidental releases, which are usually referred to as incidents. You have incidents of varying degrees of severity, and then you have the radioactivity that you have in your various levels of waste, which theoretically can be contained, but as I mentioned, we don't yet have any approved way of dealing with a very high level waste, that is the spent fuel.
How is South Africa making use of nuclear power to meet its energy needs at present?
In South Africa, we have the Koeberg nuclear power station, which is a conventional nuclear power station in the sense that we have the generation of steam, which drives the turbine. For the past few years, we are now investigating and researching the nuclear technology whereby we use gas, helium gas, to take away the heat from the nuclear core. And this is a project of national significance. It is called the Pebble Bed Modular Reactor Project, and it is investigated by South Africa.
When the new democratic government came into power in 1994, not even 40% of this country was electrified. We are now at 70%. So the new government has made huge strides in that regard. But the reality is that they are still 30% of the country without electricity. So we need to take electricity to those people. Eskom has been looking for many years now for sources of power or electricity alternative to coal. Since 1993, they have now also looked into the Pebble Bed Modular Reactor. It really started off in Germany, where the Germans built a small little 10 megawatt research reactor at Jülich, which they operated for about 21 years, and where they especially also tested the pebble fuel. It's called pebble because the fuel or the uranium is encased in a pebble like this. Then came Chernobyl and also a change in government, and the Green Party in Germany became quite strong, and they put the German government under pressure to shut down its nuclear power stations, and the easiest was to shut down the research reactors like the pebble bed modular reactor. One of the South African scientists by the name of Dr. Johan Slabber worked with the Germans in those years, and he returned to South Africa, approached Eskom and told them about this technology. Now you must realize that in 1993 nuclear was certainly not the flavor of the month anywhere in the world. So how does the pebble bed modular reactor work? Maybe I should start by explaining how the fuel works. Now the name pebble bed comes from the fuel, because the fuel is in the form of a pebble which almost looks like a snooker or a billiard ball. And the uranium is packaged in this ball in small little, tiny little kernels, each with a diameter of only 1 millimeter. That is very, very small. If you now imagine that this is the uranium kernel, this kernel will be a half a millimeter in diameter. It will now get 4 layers of ceramics to protect it. The most important one is silicon carbide, which lasts for over 1 million years and therefore will keep the fission products in there and protect it for over 1 million years. 15,000 of these kernels, now remember they are very, very small, will go into this ball. And the ball will then get a layer of a 5 millimeter pure graphite layer. To give you a feel for the power of this humble pebble, one such pebble, and it only contains 9 grams of uranium, one such pebble can generate enough electricity to supply a family of 4 for a whole year. Or to put it the other way around, you are going to need 60 such pebbles to supply a family of 4 for a whole lifetime. And that will really be the only waste that will be left, are these 60 pebbles. If you're going to use coal and you want to generate the same electricity, you will need about 6 tons of coal to generate the same amount of electricity. You will also need about 15,000 liters of water, and then a lot of CO2 and greenhouse gases and pollution will be pumped into the air. 450,000 of these balls will go into a reactor pressure vessel. Now, if you can imagine a pressure vessel that's about 20 meters high and about 8 meters in diameter, and you now have 450,000 of these balls inside that reactor. The reactor is then linked to what we call the power conversion unit, which is just a name for the turbines, the generator, and so forth. In other words, where the electricity is really generated. The helium will go into the reactor at the top. It'll go through these balls, and it'll pick up the heat that is created because of this chain reaction or this fission process, and it will then turn the turbine. It'll go through what we call a recuperator. It will actually be cooled and compressed, and then it'll go back to the reactor. When the turbine turns, it'll automatically turn the generator. The generator will be linked to the power lines, which will then generate the electricity, and that's where the lights come from. So it's not unlike, in principle, unlike most other sources of power generation. Where it does differ, though, this technology from, for instance, your Kuberg type reactors, is that apart from the fact that it's much smaller, you will not have helium like us. You will have water that, because of this, the heat that is generated will become steam, and the steam will then drive the generator, which the turbine, which will then drive the generator. The pebble bed technology uses helium because it is inert. It will not transfer any radiation. It's also non-corrosive, and non-combustible. It will not burn. And because of that, should small quantities escape from the reactor, it will not put people's health at risk because it will not transfer any radiation from the reactor. So there's a huge advantage in using the helium. A lot of people ask us, but what are you going to do with your spent fuel? And which is really the only hazardous waste that comes from the pebble bed reactor. As I already mentioned, silicon carbide is one of the ceramics that protects the uranium inside this graphite ball. And silicon carbide lasts for over 1 million years. Now, this fuel, the spent fuel, can stay on site for the whole 40 years projected lifetime of this reactor, after which the ideal solution is to take it to a deep level repository, not unlike a mine shaft, and where the radiation can then decay or decrease over time. The intention is to build a demonstration reactor at Coburg near Cape Town. We still have to go through an environmental impact process. In fact, it's been ongoing now for 5 years, but since it's nuclear, it has to be a thorough process, and it has to go hand in hand with public participation, which really means that the public and interested and affected parties and all stakeholders should be granted the opportunity to give input and raise concerns should they have any. Depending on how quickly that process can be concluded, we are hoping to start construction of this demonstration reactor towards the end of 2008 and have the demonstration reactor up and running around about 2012, and then hopefully starting with the commercial reactors in around about 2016. So what it basically means is that unfortunately the pebble bed technology is not a solution to the short-term electricity needs of this country, but it is certainly a solution in the medium and long term of the country, and a very good solution at that. For a change, South Africa with the pebble bed technology is leading the pack. We are world leaders in terms of this technology, mainly because we had the vision to start it way back in 1993. Because of that, we believe there's a huge market for it overseas, that we can export these reactors or the technology. And in doing so, it has a huge job creation potential. The philosophy or our approach is going to be to build an industry around this reactor. In other words, to manufacture as many of the components as possible in South Africa. The independent studies show that if we could export 10 of these reactors per year, that it'll create about 55,000 new jobs, and it will generate around about 20 billion rands per annum in foreign exchange earnings.
Once again, even this new technology has set off alarm bells with environmentalists.
For the Pebble Bed Modular Reactor program, they are proposing to import enriched uranium. That'll land in Durban, get trucked up to Pelindaba, where that enriched uranium is then put into the fuel balls. So you then manufacture your fuel elements. They then get trucked down to Coburg. So you've got this whole transport route where there could be accidents along the way as well. If you've got a truckload of powdered enriched uranium, that can cause very substantial environmental problems in its own right. That's outside of the operation of the reactor. One of our objections, in fact, to the whole way that the world in general approaches nuclear power, and particularly the PBMR program, is that they like to focus just on the reactor and what happens there. In the case of the PBMR, that is probably the least problematic part of the process. You have contamination of mine workers in the process of extracting uranium. You then have the potential worker health and safety issues around the enrichment programs. You have the potential for accident all through the transport routes. Then you've got the reactor, and then you've got the waste to deal with. They also love to focus just on the reactor when it comes to the potential contribution of nuclear power to mitigating climate change. Mining uranium, enriching uranium, which is a very energy-intensive process. Often that energy comes from fossil fuels. Transporting all the fuels, building the plant, decommissioning the plant, all of those things have a carbon footprint. So it is not true that nuclear energy doesn't contribute to climate change. It contributes much less than coal, significantly less than gas, but more than a range of renewable energy technologies. We have a wealth of renewable resources which can produce energy cleanly and at a rate and with a much higher rate of employment. So there's all the reason in the world to invest in renewables. They reduce local pollution, they reduce our contribution to climate change, they create more jobs, and they can be done at a scale which allows for community participation. So instead of communities simply being customers at the end of the lines, they are now participating in harnessing energy to deliver the energy services they need. They're not just customers, they're part of the projects.
However South Africa decides to solve their demand for more electricity, the fact remains that this is a precious resource that the public needs to not take for granted and use responsibly.
My view on the future is the combination of technologies. Experience shows that each technology has its own advantages and disadvantages. But if one looks at sustainability, and then I would suggest that fusion is some area that we need to explore, and it is being explored. But in terms of meeting the demand that we currently face, our only option is to pursue the technologies that are available in the market at this present time. And that includes conventional nuclear power station. And in terms of the PBMR, this is a future technology that will be hopefully demonstrated successfully in the years to come. And once that has proven itself, both from a safety point of view and from an economical point of view, it is possible that we will use that PBMR technology in the grid of South Africa.
The reality that humans face in South Africa and across the globe is this. If we want to sustain a lifestyle driven by technology and development and still have a planet to enjoy it on, we have to find a sustainable energy resource.